One of the things you can do, like I said, that you can't do with the models is you can pick it up and you can bend it to look down inside.
The penal.
And if you do, people on that side can see. The ones behind me, I'll have to turn it around this way. But yeah, the pineal gland or pineal body is this little doohickey. That's an anatomical term, by the way. That little tiny round body there, sitting on top of, there's these two big massive rounded bodies and two smaller rounded bodies. This is the corpora quadrigemina with the pineal sitting on top. That's obviously our cerebellum, like we have here. Human cerebellum is a bit different. There's two big lobes. The sheep brain just kind of looks like a chunk of cauliflower, sort of. The pons, right here, this enlarged area, and then the medulla oblongata, which sort of transitions down into the brainstem. There's some meninges on here. I mentioned that the pia mater, the innermost layer, is just kind of like a cellophane shrink wrap, and some of this fuzzy stuff that I'm peeling off here is some of the pia mater. It helps to kind of keep the blood vessels here on the surface of the brain. See, I'm peeling that kind of stuff off. You don't really have to, but you can tell that it's there. And on the bottom of the brain here, we actually have this big mass here is the pituitary of this guy that would be sitting in that sella turcica. There's some dura here. The dura is thick and white, the outermost layer. And if we peel that off, there's still some meninges and blood vessels that want to keep everything attached, but we don't need them. If you look on the inside, there's this little teeny bit of tissue here, which is the infundibulum, the stalk that holds that pituitary in place. And if you were to feel this, there is some actual bone in here. It's very hard. That's probably part of that little sella turcica, the little cup that holds the brain in place. Like right here. Here's inside here, this model, the pituitary is still sitting there in that little saddle. If we peel that off and get rid of it, right here, there's still some meninges attached here, but you see this little tiny structure here looks like a little tongue or a fingertip. That is the mammillary body. On the human brain, I think on this model, these two things, because the human, can you take that brain out and just turn it upside down? I just want to see if it looks bigger. It's kind of stuck in there. Or one of the other brains, if that one is being too stubborn. I want the whole, the whole thing. The whole. All right, it's hard to see, but if actually, maybe it's better to split. See, now on this model here, this thing here is supposed to be the pituitary. They can't show the stalk, so they've actually attached it to an optic nerve, which is not how it goes. But if you look at this half, there's a little knob right here, and there's a corresponding little knob on the other side right here. Those are the two mammillary bodies that come together, whereas in the sheep it's just kind of like one. This little bit of tissue here is actually the other end of that stalk, and right in front of them is where the optic nerves cross, the chiasma. If you look at the sheep brain here, you'll notice that it's kind of dented in on the side. See these two indentations? The eyeballs sit right there, kind of like facing outward on the sheep's head, and the nerve from this eye, would be his right eye, is going in right here. You can see these are the two optic nerves that have been cut. From this eye it goes in the left side, from the left side of the brain it goes in the right side, and they cross right there. We don't happen to have the optic nerve still attached, but when we do the eyeballs in 2 weeks, you were looking at the sheep eyes next door, you'll certainly see them. What else is there to see? The olfactory bulbs here that are obvious on the model are beaten up and missing from here. They would come out a lot further, and again, those sit right over top of the nasal cavities. I don't know if they show them. Maybe not. Actually, all these little dots on here are meant to show where the neurons run through those olfactory bulbs directly down into the olfactory epithelium in your nose. For smell, fissures, there's two of them. There's a longitudinal fissure. Somebody with dry hands, just flip that brain back over or stand this one up, please. So the longitudinal fissure separates the two halves. Since the meninges are around here, if I start to pull this apart, you probably hear it, and you could see I'm tearing the meninges a little bit, but that's separating it into, separating the fissure. And if we do this carefully enough, we'll look deep down inside here. I don't want to just yank it. And there's some blood vessels and things in here, but if we go deep enough in, you see there's a real white layer in there. See that white layer down inside there? That is actually, you split this guy in half, or this one, I don't care which. That white tissue that we can see in there. Oh, this one is down. All right, and turn this side and turn them both face up. Aha! All right. So, on this half of the brain, we can see this big ventricle, and this tissue right up here is the corpus callosum. That when we were looking down in the brain, that is what we see down in there. So it's fibers that are going right to left to connect these two hemispheres, to coordinate them. Yep, same thing there. So you see the ventricle here. Corpus callosum is pretty thick. You can see the ventricle. This side you can't see the ventricle because we have that septum pellucidum, which we'll hopefully see in just a minute when we cut it down the middle. What else is there to see externally? Probably not much. So what I'm going to try to do here is very carefully just cut this right down the middle. Ooh, look at that. Way better than last night. So here we got it. The ventricle is visible. That blood vessel. Get away. So there's that white roof that we saw when we looked down in. That's the corpus callosum. This white thing that makes the floor of that ventricle is the fornix, which is this little thinner one right down here.
So what would be this?
Yep, this part here, this numbered, what is that, 45 on there. So the big thick one up here is the roof. This is the floor. That there is that septum pellucidum, that membrane, which is intact on this half. It's not a very thick membrane. If I stretch this a little bit or try to poke through it, I am now tearing that little septum. When it's there, it prevents the fluid from this side from mixing with this side. So those are the two lateral ventricles. They are pretty deep if you kind of poke around in there. If you get overproduction of fluid that can't drain fast enough, you get fluid starts filling and stretching the brain. So there's a condition called hydrocephaly. Some babies are born with really enlarged heads because their skull bones are small and the head is really swollen.
Yeah.
There's extra fluid pressure in the brain. It can be dangerous, and they have to surgically try to put a drain or something in to get rid of it. But in a normal brain, the fluid that's in there drains out a little pore that you can't see anywhere on any of these models and goes into the third ventricle, which surrounds this central body called the thalamus. That's the thalamus right there. That's the other half of the thalamus. And if we kind of pull this up a little bit, you will see that there's a little groove or thing around it here. There's some little blood vessels and stuff in there. Those might actually be the choroid plexuses that create the fluid themselves. But fluid would drain out of the two side ones, laterals, go into the third one. And this is where it gets a little difficult to see. So on this model here, here's the third one, and then you have this aqueduct here that runs down to the fourth ventricle that's right there. On this half of the brain, it looks like the way I cut it. If we follow this around, I can see there's a little groove there that kind of looks like this. Or am I imagining it? It looks like there's a little groove there. It's better on this half. Actually, there's some on this half as well. That's part of the aqueduct that goes down to the fourth ventricle, which, if I kind of pull this open, you will see that there is actually a space between the brainstem right here and the cerebellum back here, and that is the fourth ventricle. There is, if you look at this carefully, there's a little bit, it's very easy to tear, maybe not so good there, probably not so good here either. But fluid from the third ventricle would flow down through that aqueduct into the fourth ventricle, and then eventually down into the central canal. This is beginning the central canal of the spinal cord as the medulla oblongata turns into the spinal cord. And you can't really see that well on. No, you really can't see it that well on this guy. See, now when you cut the brain that way, just like these models are cut, this is our little pineal body that we were looking at before when I bent the brain in half. And there's none of it left on. Oh, wait a minute. Oh, yep, that's some pineal gland, or yeah, pineal gland as well, sitting on top there. Other than that, there's really not much else to see, except for.
Can you see the pons on this or no? No. Oh, from the back. Oh, okay.
The pons is the big rounded swollen area. So right here.
Mm-hmm.
And then from the pons, it elongates out into the medulla oblongata. So we can see it. It's not. I mean, it's a good deal of the brain stem is the pons and the medulla. The only other thing I was going to say before you put that back together, ahead of me, is that on one piece of that, if you cut this open to see, when I was talking about the gray and white matter, you can't, actually, if we took that piece off, can you take off, what else can we take off? What do you got in your hand? Oh, that's the half of this. All right, anyway. No, and it doesn't matter. Gray and white matter. I said if you had a fresh brain, the gray matter is the outermost millimeter or two, and the white matter is on the inside. So if you look at this carefully, it's a little bit darker color here all around. It follows all the little bumps and grooves, but you see the outside surface is a little bit darker, and all the white is all the myelinated axons, myelin being rich in fat. It looks very white. This being preserved is a lot more rubbery and spongy, or more rubbery feeling because of the fixative, but a fresh brain, it would look totally different. Color, it would be a lot more delicate tissue than this is, but that's what we have.